We are going to find the volume of a solid of revolution. I'll do one video example here, and this one's going to sort of wrap together all of the main ideas. The garden variety versions of these problems are pretty plug and chug, so we'll just go right to one that has a little bit of a complication in it. We are going to take the region that's in between these three curves, y equals square root of x, which is right here, and x equals 4, which is right here, and y equals 0, which is right here. And we are going to take that and revolve it, take that region, and revolve it around the y-axis. And that's going to generate this hollowed out three-dimensional shape, like there used to be a whole wedding cake and then somebody reached in and grabbed out the center all the way down to the bottom in the center. So basically a full cylinder plus or minus a section that's been removed. Now, like with the surface area calculations, the axis of revolution dictates the variable of integration that you have to use. So since this involves the region between two curves, the outer curve, which is just this x equals 4, remember that's going to spin out of the page and into the page and back around. It's going to make that large cylindrical outside part of this volume. And then there's an inside function which is being removed, because once we get the region inside relative to the y-axis, once we get rid of this that's inside the square root function, what we have left is the hollowed out cylinder. So we're going to integrate with respect to the y-axis, which means that our functions need to be written as x equals a function of y. So the outer function is just x equals 4, or g of y equals 4. The inner function is originally called y equals square root of x. We flip that around to write it x as a function of y. So y equals square root of x is the same thing as x equals, and now it's h of y is the name, and that'll be y squared. The endpoints of integration, well, the x-axis endpoints are 0 and 4, and 0 will stay the same right there, but the upper endpoint, what we're looking for here is how far up the y-axis are we going to go with this, and the corresponding point to x equals 4 is y equals 2 because of that function. So altogether, the volume that we want is going to be an integral along the y-axis from y equals 0 up to y equals 2. We're going to look far out in both directions. What do we see on the outside? Well, we see the function 4, x equals 4. And then we're going to subtract away the inside function, which is the surface, the volume generated by the inside function. And remember, this is just like pi r squared, pi r squared. The radius of each is the function value itself. So 4 squared, y squared, squared form the two terms. This is going to be pi times the integral from 0 to 2 of 16 minus y to the 4th dy. It does say in the notes that given where we're at now, the construction of the integrals is more important than the routine evaluation. So this one, do you have to evaluate it by hand? No, you don't. But I would argue that for one that's this simple, by the time you turned on your computer, opened up some software, typed in a function, asked for the integral, and blah, 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 you could have just done the thing by hand. So the antiderivative of this is 16y minus 1/5 y to the 5th. We're going to evaluate that from 0 to 2, and that's just pi times 32 minus 2 to the 5th is also 32. And then when we plug in y equals 0, we're done. So there, we generated that exact answer by hand, faster than you could go open up software and use tech to evaluate the thing. So make sure that even though I'm saying that you can use tech to evaluate integrals once they're set up right, don't turn it into a crutch. Make sure that you understand there's a threshold where you say, I can just do this thing quicker than I can go ask a computer to do it for me. Save the computer for the stuff that really needs it.